The first speaker of our next session is Mary Gerhardinger from the University of Pennsylvania. Here she is. She's working in natural science with Mark Drodden and did her practicum at Argonne National Laboratory. And she's going to tell us, what does it take to simulate a black hole?
Yes. Thank you so much. So I'm Mary, and I just finished my 4th year at the University of Pennsylvania, and I'm studying cosmology. So I thought today we could talk a little bit about black holes. Here we go. And this is work that I just published about a month ago. There's the archive link if you're interested. And thanks to the support of the CSGF, I've actually been able to continue projects that I started in my undergraduate. And so this is the culmination of one of those. And it's been with fabulous collaborators, physicist Thomas Baumgart, Kitty Clough, Tom Giblin, who was my undergrad advisor, and then a graduate student, Amanda Miller. And so with that, I want to tell a little story today. And I want to talk about gravity, which is something that cosmologists think a lot about, right? Because that's in our universe. And I want to talk about how we can use computers and how we can utilize HPC. And specifically, we'll look at my work in primordial black hole formation. OK, so we want to understand gravity. Well, if we asked Isaac Newton, right, he'd tell us that gravity is a force. It's the thing that's pulling us to the ground. It's what keeps the apple down. But if we go a little bit later in history, to the early 1900s, Albert Einstein would say that gravity is the geometry of space-time. And I want to sit with that for a moment, because that's a crazy thing to say, right? So now let's understand this with a little bit of an analogy. Let's say I'm holding a bed sheet with these people in the front, right? We're holding it taut, OK? And then I take a bowling ball, and I put it in the middle. What's going to happen? Well, the bed sheet's going to dip where the bowling ball is, right? And then I take a marble, and I put it on the bed sheet, and I give it a little velocity. What's it going to do? It's going to orbit around the bowling ball, probably, and then maybe eventually go into the bowling ball. And now this is what Einstein would say is what's happening in our universe. In this case, the bowling ball is a really massive object, like a black hole or the sun in our solar system. The marble is a less massive object, like the Earth, for instance. And the Earth is just following the natural path by this curved bedsheet. And Einstein would say that curved bedsheet is the geometry of space-time. That's what gravity is. OK? And now this interplay between the curvature, the bedsheet, and then the stuff in our universe is really how we think of general relativity. So it's summarized nicely by this quote from John Wheeler, which says that general relativity really says that space-time tells matter how to move. In our little example, the geometry, the bedsheet, told the marble how to move around, right? But on the flip side, matter also tells space-time how to curve. The big bowling ball curved the bedsheet so that the marble could move around. OK, so if we actually want to understand this, this is what general relativity is. It's telling us how the stuff of our universe, right, the planets and the people and the puppies, is interacting with the very essence of space-time, the curvature. And this is summarized really beautifully in Einstein's field equation, which is this equation here. I only have 2 equations, I promise. But this one here tells us the curvature, which is somehow encapsulated in this quantity g mu nu. And the mu's and the nu's are indices. Technically, this is a tensor equation, which is kind of like matrices. But we won't care about that for now. We'll just say, OK, curvature is somehow encapsulated in this quantity, and matter, the stuff in our universe, is in the t mu nu quantity. And this looks deceptively easy, right? Like if I told you what t mu nu is, then you could figure out what g mu nu is pretty easily. Unfortunately, this is actually a set of 10 coupled, nonlinear, partial differential equations that we need to solve simultaneously to understand the dynamics of the universe. So it's a lot more complicated than it looks. And I've written it out in a form that cosmologists might be more used to. It doesn't really matter. But this little quantity g now describes the distance between 2 events in space-time. So this is telling us about the dynamics of space-time, what's going on in our universe. Very few situations are actually solvable, though. We really need something that's very highly specific, like, for instance, a single black hole in vacuum. Then we could find a perfect solution to this. But in other cases, we have to solve a set of 10 coupled nonlinear partial differential equations. And I think all of us in this room would say, OK, let's use computers, right? Partial differential equations, that seems like a great task for computers. This is the branch in physics known as numerical relativity. Its goal is to use computers to solve Einstein's field equations. And I want to understand what this means a little bit so that we can understand what it means to simulate a primordial black hole. So what happens in numerical relativity? Well, the basic of numerical relativity is that you want to simulate something that's four-dimensional, but that's kind of hard. So you'll split it up, you'll foliate it into 3 + 1 dimensions, 3 spatial dimensions moved through time. And this is actually quite intuitive to us, right? For instance, if I had a 3-dimensional box, it's much easier to simulate a 2-dimensional slice through time in order to get a full 3-dimensional box than an actual 3-dimensional thing, right? So this is what numerical relativity does. So within our 3-dimensional space that we're simulating, each point can shift in physical space and time between every time slice, right? This is how we actually capture the curvature of the universe. But this is also where the art of numerical relativity comes in, because you have a choice as to how exactly those points are going to shift. Your coordinate points will shift. And then, of course, we actually want to simulate something. We don't just want a blank universe. We want to put stuff in it. And so we'll split Einstein field equations, and we'll describe evolution equations and constraint equations. And those evolution equations tell us, OK, how are we actually going to take stuff and move them through the universe? How are they going to be dynamical? And so we'll split fields into volume and shape, and we'll evolve those through time. But we're also going to evolve constraint equations. And that's one of the keys of numerical relativity, that you evolve extra information kind of so that you know how much you're lying to yourself, right? Because whenever you use a computer, you're doing some sort of truncation somewhere, right? And the constraint equations are a way to determine how much are these conserved quantities actually being conserved, and how much are we lying to ourselves by using a computer. And that's really important, right? Because we need to know when we can trust computers, when we can trust the simulation. OK, so what do I actually do in my work? I use a code called Gabriel, which stands for Grid and Bubble Evolver with Relativity. And it's a lattice simulation. It does exactly what numerical relativity does. And it's designed for cosmology. It was built by my undergrad advisor, but I built a new version that includes fluids, which we'll talk a little bit about. And essentially what it does, right, is it discretizes space-time. It's a point, it's a lattice of little points. It's got periodic boundary conditions, which means that what exits the box on the right will come in on the left, and in that way simulate a very large universe, like our observable universe. But I want to stress that this is computationally expensive, right? Every point in the grid has to evolve about 25 coupled dynamical quantities on each time slice, in addition to keeping track of how those points are moving relative to each other within every time slice. And in order to have good resolution, we use about 256 cubed points so that we can trust the actual physics of our simulation. OK, so we've set up, we care about gravity, or at least I care about gravity, and I hope you'll bear with me. And we know how to do this with computers a little bit. Now, what do we actually want to look at? Well, there have been theorized that these primordial black holes exist in our universe. Now, you might have heard of black holes, right? Black holes are these extremely dense objects, so dense that light can't even escape them in our universe. But those black holes have astrophysical origins, by which I mean they're usually a star that's exploded, and then it's so massive that it collapses under its own gravity, and that forms a black hole. However, it's been theorized that in the very early universe, and by early, I mean here less than 1 second after the universe is born, actually really less than 10 to the minus 30 seconds after the universe is born, so after the Big Bang. At that time, the universe is so hot and dense. We can think of it just like a big plasma of energy, right? And so there's these little clumps of energy all over. The plasma is not perfectly homogeneous. You've got these little clumps everywhere. And so the idea is, if your clump of energy is big enough, and if gravity is nonlinear, blah, 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 then you should collapse under your own gravity and form a black hole. And we'll call those primordial black holes. So different than an astrophysical origin. But that blah, 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 blah kind of matters, right? We need to actually check. We can't just wave our hands and say, nonlinear physics. We have to actually check that you can actually form these black holes and see how large of a clump of energy do you need. That's important, right? Because if you need a huge clump of energy, well, we wouldn't just have them in our universe. We need to have realistic situations. So that's what we're interested in, and that's really the guiding question of this work. How big of a clump of energy is big enough to get a primordial black hole? So what do we actually do? Well, we set up a fluid. And you might be sitting there thinking, OK, you just described a clump of energy. That seems pretty discrete, right? And you're right. But bear with me for a second. So the question here is, if I have a ball of energy. So let's think about it like an actual ball, like a golf ball, for instance. And I want to know, how big of a golf ball do I need to form a black hole? But the universe is not just one golf ball, right? In the early universe, there is so much energy that it's like if I filled up this entire room with golf balls. And if I did that, if we tried to walk through these golf balls, it might be a little painful, but it starts to act like a fluid, right? We can understand that. It's sort of moving in a way that a fluid would. And so fluids are actually a great description for the early universe, for the energy that's in the universe. And so that's what we do. We set up a fluid that's kind of got ripples in it, like you might think of the ripples on the waves or something. And then we add a bigger clump, a bigger ripple, specifically a spherical Gaussian. And we ask, how big of a spherical Gaussian, how large of an amplitude do I need to form a black hole? So those are our initial conditions. And we satisfy the constraint equations, and then we evolve them through time, and we see what actually happens. So here, I'm showing two-dimensional output of the field, or of the code, I'm sorry. And we're looking from left to right is through time. So this is the start of the simulation. And I just want to focus on this first row to begin with. So this is a two-dimensional output of the field. And you can see it looks like there's almost nothing there, but the spherical Gaussian is just really small. Okay? And then as the simulation continues, that spherical Gaussian grows and grows and grows and grows until you can see this is a singularity forming. Okay? And so that is what we'd call a black hole. And now we actually do more rigorous tests to see if can we actually call this a black hole. But for right now, let's just look at that. Okay? But that's not what always happens, right? This bottom row, it looks identical to the initial conditions, but it's actually got a slightly smaller spherical Gaussian. And you can see that grows, and then it starts to shrink and dissipate through time. So not every big clump will form a black hole, which is what we're seeing. And this is really cool, right? So we calculate in this paper a threshold for how large of an amplitude for your overdensity do you need to actually form a black hole. And the number doesn't matter so much. C is basically a description of how large of an amplitude do you need. But it's about 0.8 is what we find. And this matches analytic expectations. So there's been recent work by Ilya Musko and other collaborators who've said that if you include nonlinear effects and you do some sort of analytic approximation for how large of an amplitude do you need, then depending on the exact shape of your overdensity, whether you assume it's perfectly spherical or spinning or whatnot, then you should have a black hole if your amplitude is between 0.7 and 1.15. So our 0.8 fits perfectly in that description, which is fantastic, right? So we demonstrated that you can actually have these simulations, and you can form primordial black holes, which is really cool. But now the question is, OK, is that realistic? Like we've seen that if you have a really big golf ball, then you can get a primordial black hole. But that's not really realistic, right? The universe is more like if you have a big golf ball next to a small golf ball, next to a medium golf ball, next to so on and so forth, right? And so the goal is now, we're starting simulations. What if we add perturbations on top of these initial fluctuations? Do we get the same threshold? What happens with these primordial black holes? And so with that, I want to say thank you to the CSGF for the support for this work, and thank you to all for listening for today.